Now we'll move on to our next conservation equation. That's the conservation of linear momentum. So now recall that linear momentum is from Newton's second law, and that's our momentum as a vector. It's important to remember these are vector equations. Is going to be our mass times our velocity. Since these are vector equations, not scalar equations, so anytime that we draw that little vector symbol, we have to remember that it has both magnitude and direction. And unlike conservation of mass, which was completely scalar, this is going to be very important for what we do. So if we take that momentum equation and we run it through Reynolds' transport theorem, we end up with an equation that's going to be in a very similar form to what we had for conservation of mass. So the derivative with respect to time of momentum, so m times v vector, of our system. Now, this is not going to be equal to 0 because we have other things acting on the control volume. This is going to be equal to the sum of all the forces acting on the fluid, acting on the control volume and everything. And so these forces are going to end up being classified as one of two things. So we have the sum of all the surface forces acting on the system. So what is a surface force? This is a force that acts on the control surface. You'd be looking at air pressures, you would be looking at reaction forces for things like bolts and whatnot, looking at frictional forces. So these are all the ones that act on the surface. And then you add to that the sum of all the body forces. And body forces are ones that act on the entire control volume at once. Gravity is a body force. Electromagnetic forces are a body force. Nuclear forces are a body force. For this class, when we talk about body forces, we're really going to focus on gravity and nothing else. And so, what is that going to equal? Just like with conservation of mass, we're going to look at the change of linear momentum in the system itself, and then what's coming into and out of the system through the boundary. So that's going to equal the time derivative over the control volume of the velocity times density over the volume. And so that's what's changing within the control volume itself. And then we're going to add to that the integration over the control surface of the velocity density times the relative velocity dotted with the normal vector dA. Okay, so now let's make our assumptions. I'm going to come over here and I'll just put them off to the side. And so we're going to assume that fixed CV. Fixed CV. So the CV doesn't change. Now, especially as we're talking about linear momentum, if we do have a fixed CV, well, we're not worrying about this relative velocity anymore either. Because the relative velocity would be, is there a difference between the velocity that the CV is moving and the velocity that the fluid's coming into or out of the control volume? And so if we tie that, we'll tie that to our one-dimensional inlets and outlets. So we make those two, and what do we end up getting? We've still got the sum of all these forces, and that's our surface and body forces, is going to be equal to ddt over the control volume, the velocity vector rho dv. Now we get into the same thing just like conservation of mass. V dot n is going to end up reducing down to just be plus v coming out minus v coming in. So we have the sum of everything. V vector rho a v scalar out minus the sum of v vector rho a v coming in. Now, I can't stress this enough, but you need to remember, one of these velocities is a vector quantity, One's a scalar quantity. One of the biggest mistakes I see with this, what students will do, is when they're solving these equations, they'll just make that v squared. It's not. Because one has to worry about direction, one does not. And you'll see that in the examples that we do. And so the last one, we can sit there and we can go, okay, I'm going to make my favorite assumption. I'm going to make that steady flow assumption. What does steady flow do? That gets rid of the time-dependent parts. That part goes to 0. So what we're finally left with in our conservation of linear momentum equation is the sum of the surface forces. Once again, these are our reaction forces, these are our pressure forces, these are our friction forces, these are all the things that act on the boundary, plus our body forces. Once again, these are the things that act on the whole body. Nuclear, electromechanical, gravity is going to be equal to the sum of v vector rho AV. And in fact, what is rho AV? You can write this even easier. Rho AV is m dot. All that stuff coming out of the system minus the sum of v vector m dot coming in. And that's our final formulation of the equation when we assume a fixed CV, one-dimensional inlets and outlets, in a steady flow situation. I actually like writing this better with the m dot because it separates out the velocities. We can calculate it at m dot, plug it back in, so we hopefully don't get confused with the vector form of velocity and the scalar form of the velocity.